Hey pre-calc students, welcome back to day 4. This is part 3. We're still focusing on quadratic and absolute value inequalities, but we're going to take a graphical approach, and they should support the analytical approach. Okay, so we'll maybe do one or two of them both ways just to make sure that we are in agreement. So the graphical approach is we're always going to use what I call the one graph method, and that means we're going to always set it to 0, which is easy. We subtract the 10. Okay. And now we're going to use that parabola, and that's what we're going to graph. And when we graph that, I'm sure you could graph it pretty easily on your own, but I'm just using a graphing calculator, which you can. It's calculator active. X squared. Sorry, let's pull it up. Minus 3x. Minus 10. Graph. Just what I expected. So what do we got? We got a parabola, and it's nice and factorable. I bet you could have done that in your head. Fraction 10, they give you 3 or 5 and 2. So that first root is negative 2. That next root is 5. Nice happy parabola. What I'm really going to do to that two-dimensional graph, x and y axis, is interpret it as a one-dimensional plus minus line. There's the root. That's one partition. There's a root, that's the other partition. Plus means above. Below the x-axis means negative. Plus. And what do I want? I want the pluses. That would be x is less than negative 2 or x is greater than 5. So that's a graphical approach showing all that work. All right, let's find another one. Again, we're going to set it to 0. 3x squared plus 10x, subtract the 8, that would make a minus 3, is less than or equal to 0, and then graph this. Sorry, I thought I had my calculator sitting on my screen. View, always in front. There we go. Y equals, second insert, 3x squared plus 10x minus 3. Happy, I expect it to be. Zoom, 6, nice and centered. Let's use our calculator to find the intersections. I like to use the y2 equals 0 method and find intersections. And second calc 5. My spider's closer to this one, so I'll remember that one. Enter, enter, enter. I'm going to sketch that nice blue happy parabola. This value right there is 0.277. I'm not worried about scale. These grids obviously don't count for 1. Let's go second calc again, 5. Let's go back this way. Spider closer to that one. Close enough. Enter, enter, enter. Negative 3.610. Always 3 decimal places. Let's again convert that to a plus minus line. I could have done it on the left where I had room. I just want to do it right below so you guys can get the hang of this. Negative 3.610, 0.277, positive above, negative below, positive above. Go back to our inequality. What do we want? We want the negative, so our solution is x, any number between negative 3.610 and 0.277, inclusive. Looks pretty good. So that's a graphical approach to quadratics. Using your calculator to find those roots, one graph method, converting the two-dimensional x-y axis to a plus-minus line, find the inequalities. I don't think I need to do that one. Let's do the same strategy, but using absolute values. So we'll go to our calculator. Clear out the old junk. I'm going to keep the 0 into y2 just in case I might need that root. How to find absolute value on the calculator is math over num. Enter. There's our ABS. 3x plus 5. Get out of the absolute values. Minus 10. Hit the graph. Just what I expected. A pretty typical V. Let's find those two intersections. One's negative, one's positive. Second, trace 5. That spider tells me 1.6 repeating, otherwise known as 1 2/3. This one, 5. Go back. Actually close enough. Enter, enter, enter. -5. Again, converting that graph to a plus minus line. Partition there, -5. Partition there, 1 2/3. Above, below, above. What did I want? I wanted the aboves. X is less than or equal to -5, or x is greater than or equal to 1 2/3. All right, sounds pretty good. That was our first absolute value inequality graphically. Now let's try to do another one. But it's got that curveball we talked about. By that I mean, by that I mean, let's calculate a little bigger, I hope. Dang it. Oh well, that's all right, it'll work. Before x over here, which we know created a non-plus minus line one time. A non-sign change plus minus line one time. Pardon me. Here's our graph approach. Bring that over, greater than 0. That's what's going to get plugged into our calculator. Y equals absolute value 2x plus 7. Get out. Minus 4x. Zoom 6. Looks kind of linear to me. Doesn't look like an absolute value v, but I know that from our base function knowledge, absolute values make v's. Watch what happens. I'm going to zoom 3, which is zoom out. And you have to hit enter another time to zoom out. So what do you actually see? You see a v, but a skewed v. And that's what that 4x does. It skews it. So it's still a v, it's just not a symmetric v. But more importantly, what it does is it creates only one partition on the plus minus line. Second, trace 5. Enter, enter, enter. 3.5. Translate that two-dimensional graph to a one-dimensional plus minus line with a partition of 3.5. Above means plus, below means minus. What do I want? I want the above greater than, so x can be any number less than 3.5. I want the pluses. I could always numerically check, throw a 0 into the original. 0 plus 7 is 7. 0 times 4 is 0. Is 7 greater than 0? It sure is. Throw a 10 in. 2 times 10 is 20. Plus 7 is 27. Is 27 greater than 40? It sure is not. So that's graphically what happens with that 4x term on the right that we starred analytically. That's how it works graphically. If we took our example from the earlier in the day, when we had that absolute value of x plus 2, pardon me, absolute value of x plus 2 is less than or equal to 3x. Again, it's got that x. I'm concerned about the sign change. Set it to 0. Let's go to our calculator. Y equals absolute value of, delete x plus 2, get out 3x, graph. Now you can sort of see that skewed V already. I can see that vertex up there. If you want to zoom out again, I wonder if it'll look a little bit better if I zoom out. Same, but it's definitely, I actually like the zoom 6 better. But you can see where that changes, maybe up above -2 for X. So what would I do graphically? I would sketch it. Partition is the root. I find that root. Enter, enter, enter. The root is 1. Plus minus line, only one partition 1. Above is plus, below is minus. I want it below. I can include that in the solution. So my graphical solution would be anything greater than or equal to 1, which is exactly what we found a couple minutes ago on one of the previous videos by doing that absolute value analytical. So we did a lot this day. We did that plus minus line idea. We did quadratic inequalities. We did absolute value inequalities, but we did them 2 different ways. Quadratic and absolute value analytically first. Partition the number line by factoring or the 2 equations. Use our plus minus techniques. We also supported them graphically. If you get the same answer, you get the same results on a graph as well as your analytical work, that means you should be pretty confident in what you did. All right, great job, guys. That is day 4 down. We got 2 more days to do inequalities. One coming up tomorrow will be on rational inequalities. The great thing, again, it's the exact same from the number line forward. The only difference is how we obtain those partitions. All right, have a great day, folks.